automorphisms of field extensions are similar to symmetries of polygons. It's not a perfect analogy, as we'll see in this video, but at this point, we've kind of seen at least one pretty good example of the complex field as an extension of the rationals as being kind of like this little line segment with the reals all sitting in the middle and then I and minus I up here and here. And we found out that the automorphisms of the complex field over the reals consist of one symmetry, one automorphism, which is trivial, which doesn't do anything, and then another that exchanges I for minus I. We call that complex conjugation. In this video, we want to look at some examples that have a little bit more meat to them. We want to look at an example of a degree 3 extension and an example of a degree 4 extension. In this example, because the extension was just degree 2, there's not a whole lot that we can do that's interesting. But we'll see that the story gets considerably more complicated once we have several roots to work with rather than just a couple. So in this video, we want to look at the cube root of 2 extended to the rationals, as well as the composite extension by the square root of 2 and the square root of 5. So for each, we want to understand the field extension by listing all of its automorphisms over the base, determining the fixed fields of each of those, and determining to what group its automorphism group, its Galois group, is isomorphic. And we can always begin by knowing that that automorphism group will be isomorphic to a subgroup of Sn if n is the degree of the extension. Let's get started with Q adjoined with the cube root of 2, every abstract algebra professor's favorite example. So, by now we know that this field really looks like a sum, a linear combination, of 1, the cube root of 2, and the cube root of 4, with those coefficients being rational numbers. Also, we can say that the minimal polynomial of this extension is t cubed minus 2, and therefore this is a third degree extension because t cubed minus 2 is irreducible by Eisenstein's criterion. So what will an automorphism of this look like? And once we've found them all, what subgroup of S3 is the automorphism group going to be isomorphic to? So as before, we kind of want to compare this to symmetries of something that has 3 vertices. So let's think of an equilateral triangle for a minute and see if we can draw the analogy. So an automorphism of Q adjoined the cube root of 2 over Q is going to be a linear transformation of that 3-dimensional vector space to itself. Therefore, it has to be representable by a 3x3 matrix in a basis of our choosing. So we're going to choose 1 cube root of 2 and the cube root of 4 as our basis. What happens to 1? Well, again, because phi has to be an automorphism over Q and 1 belongs to Q, that means that we can't move 1. So phi of 1 has to equal 1, and therefore the first column of this 3x3 matrix has to be 1, 0, 0. Now, what happens to the cube root of 2 under phi? It's not quite as simple as phi of 1 is, but if we cube both sides of this equation, it will be. Because after all, phi is an automorphism, which implies that it's a homomorphism of fields, which means I can move that cube inside of the parentheses and get, instead of phi of the cube root of 2, phi of 2. And because 2 belongs to the field of rationals, the base field, and phi is an automorphism over the base field, that means phi of 2 has to equal 2. Therefore, whatever phi of the cube root of 2 is, it must satisfy the equation alpha cubed is equal to 2. So phi of the cube root of 2 must be a cubed root of 2. Carefully chosen words there. A cubed root of 2. But we also know that phi has to belong to the extended field, Q adjoined the cubed root of 2. So now the question is, which cubed roots of 2 live in that extended field? And the answer is only one of them, namely the real cubed root of 2 that we used for our extension in the first place. The other 2 cubed roots of 2 are not real, and therefore, because this extended field is a subfield of the reals, those other roots don't belong to our extended field, and so they're off limits. So the cubed root of 2 has to stay put under any automorphism of this extended field over Q. Therefore, phi of the cube root of 2 equals the cube root of 2, and the second column of this matrix is 0, 1, 0. The same thing happens if we replace cube root of 2 by cube root of 4. Whatever phi of the cube root of 4 is, it must be a cube root of 4 in our extended field. But our extended field only contains 1 cube root of 4 because the other 2 are not real. Therefore, phi of the cube root of 4 must equal the cube root of 4, and the third column of this matrix must be 0, 0, 1. So we've actually talked ourselves into something significant here. Namely, any automorphism of Q adjoined the cube root of 2 over Q must be the identity. In other words, this triangle, which we thought we might be able to do some symmetries to, is actually glued down to the table. No symmetries are possible. So as I said, it's not a perfect analogy because we would have expected, all else being equal, that we would get some symmetries of this. But in fact, we don't, because of the strictures that are imposed by this extension not having all of the cube roots of 2 in it, but only having 1. So what's the fixed field? Well, the fixed field of the identity is always the whole thing. The identity fixes everything. And so the only intermediate field that we can possibly have here is just equal to the extended field itself. So that's not very interesting. And because that's not very interesting, the Galois group of this extension is not very interesting either. The only automorphism of the extended field over the base is the identity, and therefore our automorphism group is just isomorphic to a trivial group. It's boring. But this example, again, we milk a lot of information out of this particular field extension. It shows us that the answer to the automorphism group question is not always as clear-cut as it might appear. Even though this is a very non-trivial extension, it's a degree 3 extension of the rationals, it actually has no symmetries. It has no automorphisms over the base. All right, how about this composite extension? Root 2 and root 5, both extended into the rationals. Let's start with an obvious basis for this extended field, 1, square root of 2, square root of 5, and square root of 10. The minimal polynomial for this extension is t to the 4th minus 14t squared plus 9. I'll leave you to check that one, and that makes this a degree 4 extension. And if we go to find a matrix with respect to this basis, for 1, square root of 2, square root of 5, square root of 10, we know, first of all, that because phi has to fix the rationals, that our first column has to be 1, 0, 0, 0. For the square root of 2, on the other hand, we don't know what phi of the square root of 2 is, but we know if we square it, that we're going to get phi of 2. But since 2 is rational, phi of 2 is equal to 2. Therefore, whatever phi of the square root of 2 is, it has to be equal to plus or minus the square root of 2. So the square root of 2 can stay the same, or it can change sign. So that second column could have a minus 1 there. So it kind of seems like we're getting a reflection, similar to how we were talking about reflections before. And the same thing happens with the square root of 5, and the same thing happens with the square root of 10 for completely the same logic at this point. So in other words, our automorphisms each have the option of flipping the sign on the square root of 2, flipping the sign on the square root of 5, or flipping the sign on the square root of 10. Those choices are not independent one from another, but we do get to choose the square root of 2 and the square root of 5 to change sign or not independently of one another. So it kind of seems like we almost have 3 reflective axes here. We have a reflection across a square root of 2 axis, and a square root of 5 axis, and a square root of 10 axis. But that's actually not the most useful viewpoint for understanding the structure of this as a field extension. What I want to do now is change the basis of our extension to be a little bit more useful so we can more directly tie it to that minimal polynomial, t to the 4th minus 14t squared plus 9. To more directly tie it to that minimal polynomial, let's use as our basis the basis of the roots of that minimal polynomial, which includes square root of 2 plus the square root of 5, as well as its 3 other so-called conjugates, or 3 other roots of this same minimal polynomial, which again are related together just by flipping the signs on the square root of 2 and the square root of 5. In other words, those automorphisms that we just discovered are exactly the relationship between the 4 roots of this minimal polynomial. And our automorphisms should have the same algebraic properties, the same abstract properties, no matter what basis we choose for the extended field. So now that I have a new basis, my matrix is going to change, because that's how matrices work. They're tied specifically to the basis that you chose. But the properties of those matrices should remain the same, and so the automorphism group that we discover should give us the same information in this basis as it would have in the old basis. Now that we know what the automorphisms can do, let's see what their effect on these 4 roots of this minimal polynomial are. Well, if I decide not to flip the signs on any of my radical 2 or radical 5, then that leaves all of my roots exactly where they are. So we're going to kind of think of them as lying at the vertices of this rectangle here, and all of 4 of those vertices stay in the same place. On the other hand, if I flip the sign on the square root of 2, then looking at that rectangle over on the right-hand side, the roots that are on the right are going to flip over to be the same as the roots that are on the left. In other words, we've applied a reflection across this vertical axis if we flip 2, square root of 2, with minus the square root of 2. And a matrix for that can be the one as shown here. It achieves that permutation of these 4 roots. And thinking in terms of the symmetric group, we can represent that with the vertices numbered as they are, so the roots numbered as they are on the right, as the composition of the 2 cycles 1, 4 and 2, 3. If instead we decide to flip the sign on the square root of 5, then all of the roots on the top of our rectangle are going to trade places with their roots on the bottom of this rectangle. So that's a reflection about the horizontal axis. We can represent that by a matrix as well. Matrix that looks like this. And as an element of the symmetric group, we can talk about it as being the composition of the 2 cycles 1, 2, and 3, 4, with the roots, i.e. vertices, numbered as we see them. And then, of course, we have the option to flip the sign on both the square root of 2 and the square root of 5. If I do that, then I get a diagonal reflection in my rectangle over here on the right, and the roots trade places in yet another different way that we can represent by this 4x4 matrix. And as an element of the symmetric group, that's 1, 3 composed with 2, 4. So now we've realized the automorphisms of this group as elements of the symmetric group, and equally, actually, as symmetries of this rectangle. That's significant. So there are 4 automorphisms that we could have here, because now we've covered all the possibilities for what we can do with the square root of 2 and with the square root of 5. So now let's go through the process of determining the fixed fields that each of those elements determines. Well, the identity does what the identity always does. It fixes everything. Since every element of the extended field is fixed under the identity operation, that extended field is the fixed field of E. So I'm not even going to write it a second time. It's more interesting to talk about the fixed fields of the other elements. 1, 4, 2, 3. This was the reflection about the vertical axis, i.e. trading square root of 2 for minus the square root of 2. That's going to fix that axis of reflection. But that axis of reflection consists of all the numbers here that don't have a square root of 2 in them, that they're equidistant from positive square root of 2 and negative square root of 2, so they're at 0 square root of 2. So what is that field? It's exactly Q adjoin the square root of 5. So any element in our extended field that doesn't have a square root of 2 term in it is going to stay put under this automorphism. And so the fixed field is Q adjoined with the square root of 5 when we flip square root of 2 for minus square root of 2. Conversely, if I flip square root of 5 with minus square root of 5, the fixed field there corresponds to the horizontal axis of symmetry over in our rectangle, and that horizontal axis of symmetry is going to not have a square root of 5 component, but it might have a square root of 2 component. So the fixed field of the automorphism which trades square root of 5 for minus square root of 5 is Q adjoin the square root of 2. How about our last one, where we trade minus square root of 2 for square root of 2 and minus square root of 5 for square root of 5. In other words, I flip both of those signs. Well, what's that going to fix? Well, it doesn't fix the square root of 2, so it doesn't fix the horizontal axis. It doesn't fix the square root of 5, so it doesn't fix the vertical axis. It fixes something else. And to find out what, let's just multiply these together. Where does the square root of 2 times the square root of 5 go? Because phi is an automorphism, it has to respect that multiplication. But the product of the square root of 2 and the square root of 5 is the square root of 10, and that's the same as the product of minus the square root of 2 and minus the square root of 5. So if I flip the sign on both radical 2 and radical 5, I'm not fixing either one of them, but I am fixing their product, square root of 10. So the fixed field of that third non-trivial symmetry, third non-trivial automorphism, is Q adjoined with the square root of 10. And that's a complete description of all the fixed fields that are intermediate between our base, Q, and our extended field, Q adjoined with the radical 2 and radical 5. Now we can see that we have 3 different reflections along with the identity that make up the symmetry group of this rectangle, but then each one of those corresponds one-to-one with one of the automorphisms of our field over Q. Therefore, the Galois group of this extension is isomorphic to the symmetry group of this rectangle, because all my elements except for the identity have order 2, and I have 4 of them. That's the Klein 4 group. So this seemed like a lot of work, but this really tells all of the story that we need in order to get where we're going, because we're going to ultimately trade an understanding of the roots of a polynomial for an understanding of the automorphism group of its splitting field. And if we know how to find that automorphism group using the techniques that we've seen here, then we're going to be able to get some deep information about how the roots of that polynomial are related one to another.